I welcome you all in the 39th IIPT convention at Goa, and today I am going to deal with use of Maple in physics, education and research. Good morning everyone. Today I'll be speaking on the use of Maple in physics, education and research. This presentation highlights the multifaceted utility of Maple 2022 as a modern computational tool for both teaching and scientific explorations. Maple is a symbolic and numerical mathematical software widely used in science and engineering. It serves as both computational engine and a visualization platform. In physics, Maple allows us to handle algebraic derivations, solve equations, and model the real world phenomena very efficiently. In education, Maple works as a dynamic virtual laboratory. Students can visualize projectile trajectories, understand wave functions in quantum mechanics, or explore field lines in electromagnetism, so on and so forth. This interactive visualization makes abstract concepts more tangible. I am going to highlight certain examples from mechanics, electromagnetism, quantum physics, relativity to understand Maple features that can be showcased to students to make our teaching effective. Maple acts as virtual laboratory. Maple reduces time spent on lengthy algebra, helps students focus on physics concepts. It encourages experimentation with parameters and variables, giving a deeper conceptual understanding. By verifying results step by step, students gain confidence in solving complex problems. Beyond teaching, Maple is a powerful research tool. It can solve nonlinear differential equations, perform tensor calculations in general relativity, which are very clumsy and time consuming, and model dynamical systems. Researchers can simulate particle dynamics or test theoretical models with great precision. It has an interface that can help us to go to other languages code. Here we can deal with certain problems of solving Schrodinger's equation symbolically and simulating certain chaotic systems. We can handle a couple of problems of general relativity and an interesting animation of particle tunneling or quantum tunneling. Maple offers many advantages like cross-platform compatibility, large physics package library, symbolic and numeric hybrid approach. It supports teaching, learning and research simultaneously by saving time on complex derivations. Maple integrates smoothly with other programming languages like Python, MATLAB, and C. It generates high quality plots, animations, and 3D models that are publication ready. This makes Maple valuable not only for computation but also for communicating scientific ideas effectively. The recent version of Maple is AI powered for symbolic computations and it offers cloud based collaboration with MapleNet. To conclude, Maple bridges the gap between theory, computation, and visualization. In education, it enhances conceptual clarity. In research, it accelerates complex calculations and model development. Integrating Maple into curricula and scientific work fosters efficiency, creativity, and deeper insights. So I'll go roll you through certain modules, those I have prepared. I have referred MapleSoft documentation to prepare this presentation, and I am grateful to my own institute for allowing me to develop Maple Laboratory In the first step, we shall solve a quadratic equation. For that, I have written couple of commands, you can say, equations in Maple to save the time, and I'm rolling through the command. I'm running a restart command to clear all accumulators. Equation 1 is assigned as capital EQ1 assigned to ax square plus bx plus c, and we are asking it to solve the equation. It offers a standard solution minus b plus minus under root b square minus 4ac upon 2a. And if we write a cubic equation, we can run it for solution of the cubic equation. So the cubic equation has three roots. This is the first root, then the second root begins from here, and this is the third root. We can roll equation 1 for interactive plot, wherein we can choose all three parameters to be interactive, and here we want A to roll from -5 to +5, then B we look for from -3 to +3, and C -10 to +10. So I shall preview what is happening, and if you change these parameters, you can look for the equation. Now I can ask for the command to be generated by Maple, and this command, which is generated by the Maple, is explored for plotting, and here you can play with the parameters. If you make a negative, it opens a parabola downwards, and if a is positive, it opens a parabola upward. B will shift the equation, and depending on the situation, it offers a pair of roots you can locate at these 2 points, and C will be a y-intercept. We can explore Maple for the Bohr model, and here I have picked up theory from some resource, and now I want to write three equations. MVR, the angular momentum, is NH cross. The second equation, necessary centripetal force for circular motion, is provided by Coulombian attraction. And the third one is total energy is kinetic energy plus potential energy. We can ask Maple to solve these three equations for R, V, and N, and we can ask substitute the values of charge on electron, mass of electron, epsilon 0, and Planck's constant in our solution, so that for n equal to 1 we can generate a solution. So here you can observe the solution for n equal to 1. We have learned to solve simultaneous equations using Cramer's rule. Here we are exploring Maple to write equation number 1, a1x plus b1y plus c1z equal to d1. Similarly for a2, b2, c2, d2 components, a3, b3, c3 and d3 component, we can ask for the solution. This solution is what we write in form of determinants, Cramer rule. very quickly we shall roll through the Newton's law of cooling. Now here I am not interested in elaborating Newton's law, but I am writing equation 1 as the differential equation which states the rate of cooling is directly proportional to the difference of temperature. This negative sign indicates it is a rate of cooling. So we can desolve the equation. This is the solution of the differential equation, and boundary condition we are picking at time t equal to 0, t of 0, the temperature is 100 degrees centigrade. So for this boundary condition we can ask for a solution. Actually we need two boundary conditions because there are two constants. One is this exponential coefficient and another one is constant of integration. Now by employing these two boundary conditions, we can solve the equation. We can substitute t equal to 900, and at 900 seconds the temperature is 70 degree. So we can evaluate the constant k, and finally we write a complete equation, and at t equal to 40 we can predict at what time the temperature will be 40 degrees centigrade. It will be these many seconds, and we can make a plot, and here you can locate 40-degree temperature. So the time involved you can find out. Here we are going to consider simple harmonic oscillator, and I have written an equation for damped oscillator which is a bit complicated. We take about 1 hour's time to completely solve this differential equation on the blackboard. Here I am running a module with plots. The ordinary differential equation I am having is m into d2x by dt square plus kx, and the retardation resistance part r into velocity always. So we can solve this differential equation. This is the solution of the differential equation where C1 and C2 are unknown. So to work out these two constants coming in solving the differential equation by two boundary conditions. The displacement at t equal to 0, x of 0, x of t at t equal to 0 is 1. It means that the oscillator is at some extreme position, that is say 1 centimeter at t equal to 0, and at that point the velocity, so this d represents derivative of x at t equal to 0 is 0. So for this boundary condition I am solving the differential equation. This is the solution of differential equation, and now I want to develop an interactive plot of this solution. So plots interactive right hand side of solution. So this quantity I am picking for plotting, and this offers me animation. Actually I want three interactive parameters. On x-axis I want time. This should roll from 0 to say 50 seconds, and mass we can have say 1 kg, so that it will be the slider will be at the middle. The resistance part we can choose say coefficient 0.3 and the spring constant as 0.1. So for this I am asking Maple to generate a command. It has generated a command. This command I am taking into clip to copy and paste. So here I am pasting the command and running over it. So if I change the mass to 2 kg, what will happen? You can observe. So a kind of deadbeat you achieve here, then it is oscillating. If you choose R to be 0, it is undamped motion that leads to sinusoidal wave, and as you increase R, the damping goes up. the spring constant will and mass will determine the frequency. Omega is equal to under root k by m. So by playing with k, so this interactive sense will develop a bit better understanding of student about the equation that we have obtained out of solution of differential equation. Now the very similar equation that we have just now learned, damped harmonic oscillator, has a resemblance with growth and decay of current in LCR circuit. So here I am exploring the commands. Restart. The differential equation is R into I, that is I is dq by dt, L into di by dt, it is actually d2q by dt square, potential difference across inductor, and the potential difference across capacitor is q by c, that is equal to the total potential applied. So this ordinary differential equation of second order can be solved like this. I'm increasing the font so that you can see very clearly. Then boundary condition at t equal to 0, q of 0, that is charge 0, and current dq by dt at t equal to 0 is 0. See, this is the way of writing boundary condition. One has to learn the code, means one has to learn the language in which we are writing the boundary condition. And now we are asking Maple to desolve the ordinary differential equation 1, I mean this one, for the boundary condition this one, BCS. So here you can observe the solution. This is the solution, and this solution is being plotted here. If we change the battery potential, then the y-axis parameter changes, which talks about actually current. By changing the value of inductor, the exponential decay, you can see if we increase the value of resistance, the decay is faster. If you make resistance 0, it will be sinusoidal. And by changing value of capacitor, how the things behave, you can observe. Now I want to showcase the plots of LCR function and how the exponential parameter plays a role. So here you can see the plot of e to the power minus t and minus e to the power minus t, where time rolls from 0 to 6 seconds. Then you can see the plot of 5 times t, where t rolls from 0 to 6 seconds. And in the next function, I have written e to the power minus t into sine of 5t. So here you can see the sinusoidal wave with decreasing amplitude. Its amplitude is governed by e to the power minus t, and e to the power minus t is this function, and minus e to the power minus t is this. So the envelope of decreasing amplitude I have plotted along with actual sinusoidal wave. This is a very interesting depiction wherein you can roll through certain things. This is growth of current in LCR circuit, 1 minus e to the power minus t into sine of 25t we have plotted. Now 1 minus e to the power minus t we have plotted. So this is how the functions behave in the plot on the actual to the scale plotting. If you know the Lotka-Volterra solution, predator and prey model, you'll be able to understand the solution of this differential equation and the plot. So with DE plots and DE tools, we are running this pair of equations wherein dx by dt is equal to alpha times dx minus b times dx into dy. Then dy by dt is equal to minus beta times dy by minus beta times y of t into c times dx into dt. We can choose certain values of a, b, c and beta, and for that we can generate a d plot which is cyclic in nature. Now, to understand what we have learned in the beginning of calculus, maxima and minima of function, I have selected a very interesting function which is x cube plus 4x square plus 2x minus 1. We shall find its derivative. F1 is actually f dash, and we can solve this for maxima or minima condition. So this 3x square plus 8x plus 2 equal to 0, and for this we can obtain two roots which are actually complex here. Now we can evaluate the values of x where the function becomes 0. I mean function has maxima or minima. Then second order derivative we can find, and at maxima or minima we can evaluate its value. So the point where it has negative value, the function has maxima, and positive value it has minima. Now the same function I have generated for g, and we can plot g. You can see the function has a maxima here and minima here. So the first order derivative of the function is 0 at the point where it has maxima, and similarly at the point it has minima. Then we can see the second order derivative which is having negative value. You can observe here where the function has maxima, and positive value where the function has minima. I would like to showcase certain three-dimensional plots. We are using a module with plots, 3D plot of sin x into cos x, cos y. Then x into y we can plot, we can roll it to have a look at this. Then we can generate a plot using this very function. Similarly, sin of x plus y, where x and y has certain range. Then x square minus y square, we want to make a 3D plot in the range where x and y rolls from -1 to +1. So here you can have look at certain functions wherein we can change color scheme, and we can club C1, C2, C3, C4 to generate a plot at the same time. So this is a kind of toroidal function, and some other contour pattern. In complex numbers, we generate Julia sets, and these Julia sets offer a very interesting diagram which is generated using Maple. If you are familiar with general relativity, we can obtain Schwarzschild solution using the tensor and differential geometry library. We are choosing coordinates t, r, theta, phi, and the symmetric sparse array we can generate using a 4 by 4 matrix that has component 1 1, 2 2, 3 3, 4 4, only non-zero, and it will look like this. Now the last command gr tensors gr, coordinates g, contravariant matrix, determinant C1, C2, that is Christopher symbols representation, type 1, type 2, Riemann matrix, Ricci tensor, the scalar curvature, and the matrix we can call for display. It will offer us a wonderful expression which one has to understand by rolling through the solution obtained. So I'm going up to the place where we have asked for display of various parameters. So a long calculation that takes weeks time to generate solution is obtained in a fraction of a second. So I'm going to the top. Here we are looking for the coordinates. I'm reducing the font size. Coordinates are t, r, theta, phi. The covariant matrix components G11, G22, G33, G44, and the determinant of this covariant matrix tensor. Then we are looking for the contravariant matrix component which are non-zero. After contravariant matrix components, non-zero components, which we have seen, we are going for the Christopher symbol of first kind. Only non-zero components are displayed here. You can observe that if you define the function phi, it can obtain us values. Then the Christopher symbol of second kind you can obtain. Then the Riemann tensor non-zero components R1212. It is up to here. I'm trying to hold that. This is R1212, R1213, so on and so forth. You can observe. Then the Ricci tensor non-zero components R11, then R22, then R23, then R24, so on and so forth. The Ricci scalar you can observe here, capital R equal to. Then the Einstein tensor having non-zero components G11, G12, so on and so forth. Similarly, the Weil tensor C1212, so on and so forth, you can obtain in a click. Now, if you define a function phi, then it will be able to offer us the desired solution. Now in the same worksheet, we will go ahead for a geodesic equation using Christopher tensors of second kind. So this is the only additional command I am having, and I am rolling the entire worksheet for execution, and here these additional equations for geodesic. This is the first one, then the second one is up to here, then the third one is this, and the fourth equation is like this. So this is how you can obtain the geodesic equations. Now here, I'm going to refer to Professor Wang's book where he has handled the problem in the polar coordinates and he has tackled the equation to plot actually the geodesic equations. So the programming begins at this point. He is defining a function as appearing on your screen and he is putting some variables to eliminate certain things to simultaneously solve some equations, and then he is exploring those equations for plotting. I have precisely followed the steps he has used in his book to generate a plot. For plotting on the scale, m, g, and velocity of light is considered unity, and some scaling equations have been displayed to generate the effective potential energy plot. And animation is developed so that we can see the role of a particle in the gravitational field. And this is the final animation I'm depicting in front of you on the screen. Thus, in this way, Maple can be explored for a variety of purposes. Thank you very much for listening up to this lecture.